In Module 2, we'll cover the main 4 rules of differentiation. This will involve stating the rules, then working through examples for each one. You won't need to be able to derive these rules. They'll all be on the formula sheet attached to the mid-semester and final exams, but you will have to be able to apply them. We have the sum rule, the product rule, the quotient rule, and finally the chain rule. The derivative of sums is the simplest case. We just differentiate each term separately. We have two functions, little f of x and little g of x, both of which must be differentiable. If that's the case, then the sum, f plus g, or the difference, f minus g, are both differentiable. We call that combined function capital F of x. Capital F prime x is simply the sum of little f prime x plus or minus little g prime x. Here we have an example. In this case, f of x is equal to 3 times x to the power 8, and g of x is equal to x to the 100 divided by 100. We saw that in example 2. So we have our derivative. We can split it up into two parts, d dx of 3x to the power 8 plus d dx x to the 100 divided by 100. So there we have, it'll be 3 times 8, x to the 8 minus 1 plus 1 on 100 times 100, so bring down that exponent, times x to the 100 minus 1, and so it's 24, x to the 7 plus x to the 99. With the product rule, we have a function that is the product of two separate functions, again f of x and g of x. The first derivative is the sum of two products. The first product is f prime x, the first derivative, times g of x, so that's our original function, plus fx, the original function, times the derivative of g of x. The textbook shows how to derive the product rule using the Newton quotient, if you're interested in seeing where it comes from. Here we have example 4. Of course, in this case, we could simply multiply these two functions, the f of x and g of x, together and use the sum rule. But as we'll see when we tackle other types of functions, that's really the case. Here we have the product rule that we want to apply, and this is our function. We'll go through the process in more detail, and perhaps you'll need to once you get a little bit more used to doing these things. We have little f of x is equal to x cubed minus x. Well, that implies that f prime x is equal to, well, that'll be 3x squared minus 1. G of x is equal to 5x to the 4th plus x squared, and then g prime x is equal to 20x cubed plus 2x. Now we have all our components for the product rule. So we have f prime x is equal to little f prime x times g of x plus f of x times g prime x. Substitute in for those values. We'll have 3x squared minus 1 times 5x to the 4th plus x squared plus our original function, little f of x, x cubed minus x times g prime x, 20x cubed plus 2x. We can multiply those out, and we get 35x to the power 6 minus 20x to the 4 minus 3x squared. The quotient rule is a little bit more complex than the product rule. Whereas with the product rule, we could swap little f of x and little g of x, and it wouldn't make any difference because we have the plus sign here. For the quotient rule, the order is important. So again, if we have little f of x and g of x are both differentiable, and of course the g of x isn't equal to 0, as we'd expect, the first derivative is a quotient. In the numerator, we have the first derivative of the original numerator times the denominator minus f of x, the original numerator, times g prime x, the first derivative of the original denominator. That's all divided by the original denominator, all squared. We can derive the quotient rule using the product rule. Again, that's in the textbook if you'd like to look at that. A simple example. First of all, we can get this into a more familiar form. So we would have capital F of x is equal to 3x minus 5 on x minus 2, where little f of x is equal to 3x minus 5 and g of x is equal to x minus 2. Again, we can find the first derivatives. So little f prime x will just equal 3, and little g prime x will equal 1. So we substitute those values into our formula. It's always useful to write out the formula. So it will be 3 times g of x, which was x minus 2, minus f of x, 3x minus 5, times g prime x, 1, all over x minus 2 squared. We can simplify that. Simplifying the numerator, we'll have 3x minus 6 minus 3x, well, minus 5 will be plus 5, over x minus 2 all squared. And so that'll equal, well, our 3x's will cancel out, plus 3x minus 3x, and we'll have minus 1 in the numerator, x minus 2 all squared in the denominator. The last of our rules is the chain rule. We use this rule when we differentiate compound functions, that is, functions of functions. The general form of a compound function is this. So we have y equals, well, little f of g of x. We have two functions there, an inner function, g of x, and then an external function, f of g. Let's consider a more concrete example. So here we have y equals a log of x squared plus x. Here the internal function is x squared plus x, and the external function is the log of that. Let's call x squared plus x u. And then y is equal to the log of u. So effectively we have two connected functions. Remember, we can think about derivatives as rates of change. What we want to find is how y changes as x changes. Here we've got the x's, and in our second function we have the y. The change in y with respect to x is dy dx. How does that come about? Well, when x changes, u will change, so we'll have du dx, and then when u changes, y changes. So we have dy du, and that's our chain rule. Dy dx is equal to dy du times du dx. So we have the change in u with respect to x, and then the change in y with respect to u. Here we have our chain formula set out. Another form that some of you might be familiar with is this. If we had y is equal to au, where u is a function of x and u is differentiable, then our chain rule could be represented in this way. Here we have a more formal definition of the chain rule, crossing all the i's and dotting all the t's as mathematicians prefer. What the other forms that we just looked at lack is that they don't specify a particular point. We define our function of a function. First we specify that function g is differentiable at point x0, and then we specify that function f, the external function, is differentiable at u0. That means our compound function is differentiable with respect to x0. This is our chain rule in a slightly different form. We have dy du and then du dx in different forms. Now let's look at an example. Since we cover the differentiation of log functions in the next module, we'll look at something a little simpler. We want to find d dx of 10 over x squared plus 4x plus 5 to the power 7. We can rearrange that to start with to get it into a simpler form. Let's say y is equal to 10 times x squared plus 4x plus 5 to the minus 7. So here we have a function of a function. Here we have the inner function, so we'll let that equal u. Let u equal x squared plus 4x plus 5. So that implies then that y is equal to 10 times u to the minus 7. Du dx will equal, 2x plus 4. Dy du will equal minus 7 times 10, so it'll be minus 70, u to the minus 8. Dy dx is equal to dy du times du dx. Just substitute in for those two values. So we'll have minus 70 u to the minus 8 times 2x plus 4. Well, we can't leave it there. Our u is just a dummy variable, so we need to replace that. Recall, u is x squared plus 4x plus 5. So we'll have minus 70 times x squared plus 4x plus 5, where we had u, to the minus 8 times 2x plus 4. We should get this into the simplest form, so we'll have, in the numerator, we'll have minus 140x minus 280 over x squared plus 4x plus 5 to the power 8.